Hello, everyone. I'm Arno Candel, the CTO of H2O AI, and today I will be presenting our integration work between open source H2O and Driverless AI. And all of this will run on our H2O AI Hybrid Cloud. And this is a great privilege because it's one of my first presentations showing all products at once. And of course, this is, as always, a great teamwork, and our team is growing. And we're hiring, we're very excited, the future is bright, and we're really proud to show off all these capabilities. So let me share my screen. Short background before I do that. I've been at H2O since 2013, so a quite long career there, and I started as a regular software engineer. I did another startup before. I was one of the first engineers there as well. Also machine learning. So I have about a decade of machine learning engineering experience and about another decade in physics, in supercomputing, as I was working with the Large Hadron Collider team at CERN, and then also with Stanford's Linear Accelerator Center where I worked. So basically I've been in the Silicon Valley for the last 15 or 16 years, and I really love programming. So I do this all day long. I'm still very much committer of driverless AI. All day long. We're always enhancing all the pieces there, all the logic, machine learning, tips and tricks and statistical, finesse here and there, how to optimize stuff, how to make it fast, how to make it, magical. So if anything is not magical, please let us know. We would love to fix it and improve it. We're makers, right? Makers gonna make. That's the t-shirt we wear. And we are very open, right? If you have any feedback, we would love to hear it. Don't hold it to yourself and say this is weird or something. Just tell us, give us comments, and we'll improve from there. So I'm gonna share my screen. You should see now slide deck here, and hopefully you will see here that we have two products. Over the last few years, the company H2O AI, not H2O, but H2O, like water, has built two platforms. Both are able to do AutoML, automatic machine learning. Open source H2O on the left side is built in Java. It's very fast, scalable, distributed, in memory. So imagine you have a 20-node cluster of machines. All those share the work to solve a machine learning problem. For example, to fit a gradient boosting machine on the gigabyte or terabyte of data. And that is fast because it's all in-house, right? We wrote it all in-house. Every line is optimized. Every line is profiled for thousands of commits. And in the end, you get a production artifact out that's Java. So you can run the model in the end on a laptop that's Windows, for example, or in production on an IoT device, or in a data center in Spark, Snowflake, wherever you want. So this is the power of open source and H2O itself. It's really an amazing platform. But then a few years ago, we said, well, all the data scientists are using Python. They do TensorFlow, PyTorch, sklearn. They're building all these for loops themselves and doing cross-validation in a particular way. They're doing time series with pandas. They're doing all these different things that you cannot easily do in Java unless you implement everything from scratch. So we decided to build a Pythonic machine learning platform that is a little bit more automatic data science than just automatic machine learning. And it can do, as I said, time series, it can do images, it can do text, NLP, it can do, more statistical things, let's say, with data, with unstructured data, than just a table of like a large Excel table. In the end, you still will give us something that looks like a table, but it could have text in a column or a pointer to an image or a pointer to an audio file or something like that. So driverless AI is really a more general purpose machine learning solution that has the ability to be extended by the data scientist users themselves. So if you want to write a recipe in Python, you can write it yourself and stick it into driverless as it's running. And that is a Python extensible recipe architecture. So with Python, you can do anything basically. And you can do a PyTorch recipe with a special word embedding for, some bird model that's in a special language, and you can just stick that in. And for the things that we built, most of our built-in transformations of the data and models have a mojo as well, which we call the production artifact. And it's also in Java. Some things are only in C++, but many things are in Java. So the entire feature engineering pipeline is in Java, apart from some of the things that are Torch and TensorFlow, but even those can be called from Java via the Java native interface, JNI, because Java can call C++. So there should be no limitation for you to deploy anything that is done in Python, but then you deploy it in Java or C++, which is quite remarkable that our team was able to translate Python data science code to production Java, production code, as I meant. So it's really powerful, and it's also very accurate because our over 20 Kaggle grandmasters have helped contributing all their smart tricks and tips, right? Like how do you do cross-validation? How do you do target encoding? How do you do, the statistical checks for whether something is shifted over time or not? And what lag should you build for a time series and so on? All these things have gone into Driverless AI over the years, and we have even more commits than open source H2O, and both have more commits than, like, say, Spark, Apache Spark. So this is a quite prolific company. Now, when you look at open source and driverless, open source looks something like on the left, right? You take a model, you say fit it on this data set, and you get a variable importance table, and you get some kind of score predictions, just like you would expect from a machine learning platform. It can handle any size data if you have enough cluster size memory. You don't need as much disk, you just need memory. So the more memory you have on your combined cluster, the better. And you can fit terabytes of data. And we have large corporations, banks, and so on. They fit the whole fraud model all at once on all the transactional data. They fit that on a 50-node cluster, right? And out comes a Java production artifact that they can put in, deployment. Now, Driverless AI looks more like on the right side. It's roughly speaking the same thing. Over time, it gets better. You see there the yellow dots going up. That's the AOC score, getting better and better over time. Even open source on the left, H2O, can also get better and better over time because it has an automatic machine learning component, which does the same thing, just doesn't visualize it like this. But what is special about driverless is the variable importance there. It makes new features. It doesn't just show you which features are important, which columns of the original data are important, but it shows you what it can make out of those columns. So the original columns were called V50, V125, V56, and so on the left. On the right side, you see that only a few, here in this case, only one feature is actually the original one, the V50, because that's the top feature. It can be used as is because it's numeric. All the other features here are combined with other features. Cross-validated target encoding, cluster distances, weight of evidence, frequency. These are some of the top features that are created out of those original columns. And when you take this 7-way interaction here, so you take 7 columns, you make one column out of them by putting all their values together and string concatenating them. You can imagine like that, right? Like zip code is this, number of car is this, number of children is this, job description is this, and then it becomes a long, massive category like by itself. The many more possible values, right? The cardinality grows, of course, by doing these interactions. And now you have a lot of possible choices of this 7-way interaction. And for each of them, we say, well, what's the likelihood if you have this particular string, what's the likelihood of you belonging to that target outcome, yes or no? And this is done in an cross-validated way out of fold. So you cut the data into like 5 pieces, and for all of the 20% pieces, you ask the other 80 for the similar groups, what is their outcome on average? And then you have to smoothen it because sometimes you only have one in one of those 80% pieces. You can't really do statistics with one thing. So then you go back to the mean, the global mean, or maybe a hierarchical mean of maybe only a 6-way interaction or a 5-way interaction, and so on. You can imagine you can do a lot of statistical things given those groups. And open source doesn't do that as much. at least not by itself. Now it can make those same target encoding features too, but you have to tell it what to do, right? And normally you don't tell it, oh, do this interaction, this interaction, this interaction. Normally you want the system to figure it out. And that's what Driverless AI does. It's really good at figuring out these interactions. It has a genetic algorithm, particle swarm, Monte Carlo, all these techniques built in. It's GPU accelerated. It does nothing else but churn through thousands and thousands of those features and models to evaluate the overall fitness of the pipeline, okay, on this data set, given your custom scorer, if you want. So you can customize the transformers, the models, the scorers. Like if you want to not look at AOC, but at something like F1 for the minority class in your 7-class problem, you could do that too, right? Everything is customizable in Driverless. So it's really just an optimization machine. And for that, it is very good. Now, imagine you can put those two together. And that's exactly what we've done here. Imagine you can take a massive data set here in the top left, terabytes. You stick it into open source on this 20-node cluster. It gets spread around, distributed in memory, you know, parsed. All the columns have a meaning, have a name. All the chunks, the pieces are sitting in memory on that machine, on that distributed machine, I should say, on that cluster. Now you can say, hey, give me a sample, make it into 5 gigs or 1 gigabyte. And that sample gets sent over to Driverless. Driverless says, okay, looks nice. Let me run some, 500 models on it with each 300 features. So you get tens of thousands of features created from those, from that one sample, whatever many columns it has. Doesn't really matter. Like if your data set has 20 columns, we can still make 10,000 features from it. Depends on what kinds of columns they are. If they're all numeric, then we can't do as much. We can do binning, we can do computing means after grouping by other bins, and you can do a little bit of things with numerics, but if it's categoricals, you can do a lot more. And together, if you have categorical and numerical data, or maybe text and image as well, or dates, you can do more, right? You can extract the day of the week and then do an interaction of that with something else and so on. You can imagine what you can do. We can have multi-layer feature engineering as well. So you can take the day and, maybe it's something that's binned, and then you can make a next layer thing and say, if it's Friday and you're in this age group, then, this and this behavior. And of course, the model can also figure that out with decision trees and so on. But sometimes it's more statistically meaningful if you make a feature out of it and present it to the model. Then the model doesn't have to spend tree splits, for example, or neural network, connections to learn all that stuff. You can just give it to it and say, statistically, it makes sense. So why don't you just use it? And that's basically the secret sauce of Driverless, is to make all that upfront knowledge so that the model has an easier time spending its time on signal extraction versus signal detection. Now, deep learning can find some of it, but usually not ever as much as what Driverless can do. So if someone says, oh, you don't need feature engineering because you have deep learning, I spent 5 years on deep learning alone, right? Implemented H2O deep learning. I can tell you it's not as easy, like even categorical embeddings and so on. All our grandmasters will agree with this. Deep learning is great. It can do a lot of things, especially in composition with gradient boosting and other methods in an ensemble. But all by itself, it rarely is the winner. Sometimes it can be, but not always. But anyway, let's go back. So Driverless figures out what to do on the sample. It spits out a feature engineering pipeline. It says, hey, do these 100 combinations of features because they have more signal than the original data. And that itself is a mojo as well, a production artifact in Java. So Driverless gives you something, or in this case, it gives it to open source H2O. It says, here is a thing. When you run it inside of this in-memory machine, every row of raw data gets converted to these 100 magic features, row by row. You take age, zip code, job description, turn it into these 100 features based on all these interactions and statistics. And you do that for every row. Now you have a new data set in memory that is enriched. We call this enriched data on the full terabyte. Now you have maybe a 2 or 5 terabyte data set in memory, just created woof in seconds, because it's all MapReduce. Like every little core of that whole cluster is busy making that transformation. It's completely parallelized and fast. So there's no faster thing on the planet to do this conversion. Now, when it's done, you have a massive data set here. And guess what? Well, yeah, you can build a model in open source, right? In H2O, because it's already in memory, it's already distributed. The algorithm is just another MapReduce that runs over that data in memory in a distributed fashion, and will say, well, let me make some splits based on it, 3 splits, for example, or a deep learning model, or a random forest, or an SVM, or a linear model, or you can do all of them. You can do H2O AutoML and say, let it run overnight, tell me what's the best model you can build. But the point is that this enriched data was created in almost no time by driverless, by using its capabilities at its fullest, right? Figure out what works and tell me what works, and automatically send it over and create this enrichment. So driverless did some sanity checks as it does work on this sample. It says, hey, wait a second, this is all garbage, something is not right. It could tell you that. It could say, look, these are the top features. Let's make some new features. And then it will say, well, if you make a tree that's a little bit deeper, it's better than a shallow tree. So we can even learn from driverless what kinds of tree are best. However, I don't recommend that right now because it's not on the sample, right? So usually to figure out that age and income matters, let's say, is more meaningful than the particular exact parameters of the tree that was fit on that sample. Because H2O will have its own tree algorithm run on the terabytes. Like, it's better to let that guy optimize instead of trusting blindly the sample model. But the features you got from driverless, you just have to take them because you have nothing better. There is no one else who gives you better features, right? So you have to trust that this transition process works, that these features that were useful on small data work on big data. And you can, of course, experiment with how much you sample. Maybe you don't sample that much. Maybe you only sample down 10x, not 100x. And then you wait a little bit longer for driverless. Driverless itself can also be distributed, also multi-node and multi-GPU. It can do big data work, right? But it's not necessarily the best way, because what if you have 1,000 things to try and each thing takes 10 hours? It's not efficient. It's better to run it on a smaller data set and then just get the insight. So there is a trade-off of how much time you spend on, feature engineering, evaluation, and, optimization versus how much juice you can squeeze out in the end. And it's all like this 80-20 Pareto optimal principle. Again, like at some point it's enough, right? And we are trying our best to make this all automatic so that in the end you get not just an H2O model that was fitted, but a full end-to-end pipeline that you can put to production. So that pipeline will say, okay, give me age and income and zip code. Let me make those 100 extra smart features using H2O driverless's Mojo. Then once you have the 100 features, you throw them into open source. That also has a Mojo. It says, oh, make me 5 more features, because maybe it had to do feature engineering on the big data. And that's actually the case. Target encoding, for example, the mean of everybody with 2 bedrooms and 2 cars. That mean, you don't want to compute the mean on the sample. You want to compute that mean on the full data, right? So driverless actually tells open source, hey, compute the mean of these groups of the target by grouping, after grouping by these groups on the full data set. And that is a new feature. So open source also makes its own features. And for that, there's also Mojos that say, oh, you want to know that the mean outcome for this group? I have it here in the lookup table. So this lookup table gets stored in the Mojo as well. So once you have the 100 features from driverless inside of H2O, then it says, make me more. So maybe now we have 120 features. And all of that is codified into these Java deployment pieces, right? So there will be something that makes first the 100 and then another 20. And then there's something that says, now I'll make a model prediction from the 120 things. Those are usually numbers. From the 120 numbers, I'm going to now make me an H2O3 model prediction. Some of them can also be categoricals, because open source can actually handle categorical data natively. It can do, if you're one of these values, go left. If you're one of these values, go right, for example, in a tree decision. So you can imagine all of this comes out in a row by row prediction. So your age, zip code, income, whatever goes in, and inside it makes the 100, then the 120, then the prediction, and out comes the final prediction value. If this wasn't clear, I'll explain it again later. So this is how it would look like. This is a real data set, just a small data set. I ran this, and I'll show you a demo on this live soon. So this is what H2O3 would look like on the normal data, right? 74 cross-validated AOC. I'm not showing tests AOC here, but for now it's just cross-validation metrics. So it's the scores on the 20% pieces averaged after you have trained on all the 80% pieces. So it's a fair estimate of the performance of the model, assuming the data is identically and independently distributed. So it's kind of the best guess of the score you would get. And these are the features that matter. It's same as what you saw earlier. Now, when you do this on the enriched data, look at the 74 going to 77. So you got a 3-point boost in AOC. It's one of the top metrics for binary classifiers, in case you don't know. That is quite a lot. And it's the same model parameters, everything. So I'm not saying this is fully tuned, but you can imagine once you have 103 GBM, it doesn't just jump by 3 points just because you didn't get the right tuning done. This is a quite significant jump, and that's because the features were significantly more juicy, if you want. There's more signal in them. And you can see here, all these string concatenations of these 6-7-way interactions are being passed to open source. And then the underscore TE is what we append here to show that it was target encoded by open source H2O. So open source was given the interaction of all these features by the driverless mojo. It said, put them all together and take them and do a target encoding on it, on the big data. And this is what open source did. It said, okay, I'll do it. If you say so, I'll do it. And then, wow, it actually helped. All these target encoded features, they helped tremendously for this data set. This is the BNP Paribas data set, for which driverless does really well. It actually lands in the top 10 or so in Kaggle out of the box, because of all these higher order interactions that matter so much. And how did it do it? Yes, you guessed it right. It was the feature engineering with all these higher order interactions. See, you can see weight of evidence, target encoding, original feature here, unaltered, just a regular feature, truncated SVD as a dimensionality reduction technique. You take all these features, this 8-dimensional space or something, and then you take one particular component of the dimensionality reduction. So maybe you squish it from 8 features to like 2, and then you take the second column. That's what this does. It's just a projection. And numeric to categorical weight of evidence. So it's even binning some of these numeric columns, and then computing weight of evidence, which is something that's looks at the outcomes and ratios and logarithms of those, and so on. So in the cluster target encoding, so it makes clusters, and then it looks at each cluster and says, what's its most likely outcome for the rows that fall into this cluster. So there's quite some sophistication in all of this. And as you can imagine, all of those are in Java, automatically generated for the application inside of open source. So Driverless AI tells H2O what to do, right? It says, here is a Mojo feature creation artifact that you can apply row by row on the full data. You just take it and apply it. Make the clusters, tell me the likelihoods, or just make the clustering itself, and then you have a cluster ID. And then you, the open source, you have to then target encode it, for example. Or here is a dimensionality reduction projection matrix, you need to multiply those 8 columns by to get 2 columns. That would be an 8 by 2 matrix that we provide. And sometimes it's good enough to make that matrix on the sample and just apply it, right? The projection is not going to change that much if you do it on a terabyte versus on a gigabyte. The evaluation of the projection itself, which one is the best, doesn't really matter. As long as you're seeing it from the right angle, it's good enough. You can do date conversions, text conversions. You know, if you have something like an image input, then open source wouldn't know what to do with it until you actually gave it, you know, this mojo here that says, given this image, turn it into some numbers that tell you how likely it is to be a cat or dog or mouse or whatever. And then that number now is available in open source. And then we also tell it what to do. So for example, we say, here are these, 6-way interactions, please go and target encode them. So group by them, figure out for each group, what is the outcome likelihood in an out of fault fashion. So then in the end, as I mentioned, you get the 3 different mojos or even more. Like one mojo comes from Driverless, right? It says, give me the mojo here for this. Normally it's a mojo for the overall pipeline that also has a model at the end or an ensemble of models. But there is a special mode that you can run Driverless in to say, no, I just want the features. I want a mojo for just the features. And that's what we do here in this recipe. Out of the box, we tell Driverless to behave like a feature engineering maker, nothing else. So this feature engineering mojo gets put into open source. And then we also say, now that you have these string concatenated features that come out, these are the outputs here of this mojo from Driverless. It just says here, I'm going to concatenate them. Others are like the clustering or the weight of evidence and other things that are also created. But in this picture here, you just see the string concatenations because this is the target encoder mojo itself that you can get. It only cares about these features that it had to target encode. So this is the set of features that we told open source to please group by and compute the means and then store the lookup tables of those means. And that's what you get here in the mojo. And so one could run this and just get the mapping from here to these target encoded means. So this would then say for every number of cars and job description, what's the outcome likelihood, like 0.3, 0.4, just one number for each. That's just the best guess we can do, statistics, right? And that itself isn't what you want. You want it to be all connected by us, right, into one big bucket. I'm just telling you what happens here. So there could be multiple such target encoding or clustering or dimensionality reduction models in H2O because it has several of those transformations that it can convert to a mojo as well. So it doesn't have to be just target encoding. You can also drop this and say, I don't want any target encoding. Like it's not necessary, but I'm just showing you that even open source can do certain transformations and feature engineering things and create a mojo for it. And then obviously, as you know, open source makes models, so they give you a mojo for the model predictions. And if you connect all 3 together, which is work in progress right now, it's committed, but not demonstrable right now by me, at least. Someone else, Michael, probably could show us how it works, but for the sake of this demo, I'm just going to show you that we have all the individual pieces. They just have to be stitched up together. So one could run them each in sequence in Java and say, make this, 100 features, add the extra 20, and then feed it into the last one and get predictions out. One can do this by hand. It's just not as much fun as having one mojo that just does it automatically. So the connection of the 3 pieces is now being done by us too. And let me give you a quick summary and some more details. So what happens when H2O gets this mojo from Driverless, right? We are saying here is a transformer and we register it at runtime. So we upload the mojo from Driverless that makes these 100 magic features. And we say, this is a new transformer. This is the name for it. Please register it. And then we can say, now run this UDF, this universal data function, and just apply it to your data. And it will just convert the original features into the 100 numbers that Driverless said are useful. But somebody still has to decide whether it should do more, like target encoding on these other things, or whether it should drop some columns, or whether it should, how big a sample it should send to driverless in the beginning. All that is done by this big data recipe. That's a program we wrote that does this whole integration, right? It's a Pythonic script or several scripts, a library that connects driverless and open source. And we built this. This is H2O's work, right? So we connected the two pieces, our own two platforms, and this is basically the script writer, the controller of the movie, or whatever you call it, the director of the movie says, you do this, connect them, and so on. So this is how it works. It's this driver program that is the big data recipe, if you want. And it works for regression, binary, and multinomial, not for time series right now, because there is no lag feature in open source for which we can get a mojo and so on. But I think we can work on that too if it's requested. For now, it's just for regular IID data. So, anything that's not strongly time series, basically, or has been converted from time series to IID outside by creating these lags and so on. You can always frame it as an IID problem before you give it to a machine learning model. So it's not a massive problem to not have that, but sometimes people want everything automated, right? In that case, we have to spend more time to automate the lag creation, for example. So the roadmap items are that we connect all these modules together for you. Another thing is the Spark pipeline. We have a working prototype where the whole thing can be turned into a Spark pipeline. Then you don't even have to connect these modules. You just tell Spark, this is what you do in each stage, and then it calls the running H2O instance or the cluster and says, do it right now. So it's basically not mojo based, but it's a in-memory monster, machine learning distributed system based pipeline. But there could also be a way to say it's a mojo based Spark pipeline, I'm sure. So because you could say, here are all the mojos, stitch them up as a Spark pipeline. And Michal will be able to answer more questions if you're asking about Spark pipelines, but you can believe me when I say that all of it is Java, so it's perfect for Spark, and everything is scalable in the end, obviously, because it's a row-by-row transformation, so you can just massively parallelize it on a Spark system. Once H2O is done with its two pieces, you connect it up, then you can just deploy it anywhere. And the beauty of the Spark pipeline is that you can even do the fitting of the whole thing in the Spark pipeline, where it will, when you say fit, it will actually call H2O and do some of the work, right? You start basically at where the driverless mojo comes in, and then wherever H2O3 would do the work, now you let Spark do the work via sparkling water, our connector to our own open source pieces. Spark can basically see H2O and control it. And in return, it gets the results back as something it can embed and run. So you can have a Spark experience, Spark ML pipeline, just like a normal one. And I think that's going to be useful too for some people. So the question then is, who decides what data goes where, when, what settings for driverless, what features should be created. So there is a need to automate some of this smart logic because it's otherwise too many choices. And also there is an ability to make an app out of it, since we have a Wave app store that I will show you in a second. That is also really cool to turn this whole thing into an application you can just click through as a user, and you don't have to write code. So this is the demo, and this is how it looks like. And obviously, the whole team is moving forward now with the H2O Hybrid Cloud. So you will see much more focus on that in the months coming ahead. Even now already on the website, we don't talk about Driverless AI as much. It's mostly about this integration. So this is a corner piece of our integration story. And it's definitely fun to build applications in Python. So all these GUI pieces that you see here, this entire application was built in Python. All of these charts, everything Python, and it's an interactive real-time dashboarding solution. low code. So you can see it on 2 different computers. If I click here, the other one will show me live updates and so on. Like, it's really cool. Prithvi and team have done a tremendous job on building this Wave platform. And so my demo now will start. How much time do I have? 10 or 15 minutes, perfect. So I will show you exactly what it looks like. Let's see, make this a little bit bigger here. So this is a finished experiment that I ran earlier. You can see the 74 turned into 77. And you see some charts. You can see there's a variable importance for each feature. That's the original H2O model. And then here are the crazy features that Driverless helped make. And now it has a higher AOC. And I ran this again on another run, and it also got 75, 78. So it's the same 3% boost every time you run it, more or less. And now we will do this ourselves, okay? So imagine you are signing up for this, H2O AI Cloud. So first, let's go to H2O AI, our website. You can sign up right here. No credit card, no nothing. You just tell us who you are, and you can use it. And this is a hosted trial. So it's on our systems in the cloud. And obviously this thing will work for you anywhere, any of the 3 major clouds, Google, Azure, Amazon, and also on premise, right? This is a hybrid cloud. So you can run this whole app store that I'm about to show you yourself on your machines, wherever you want. But it's our software. So this is the app store. This is what we are now talking about all the time. And we say we have apps. This is a lot of apps, right? You can see they go from churn to, insurance, to COVID, to interpretable machine learning, to, images, and so on. Predictive maintenance, inventory, image, another image one, healthcare, LIBOR, transition, help. We use it ourselves for measuring the speed and accuracy of our models. There are apps that convert neural nets to linear models, locally linear, piecewise, little linear models, so we can better interpret them. Model validation, adversarial robustness. There's a lot of models you can imagine. And if you can write Python, you can write these apps. And we have very good data scientists and very good solution engineers, but we've seen everybody being able to just, hack models in a day. Just show up, make something, iterate, and it's all Python. You don't need to know TypeScript, HTTP, whatever. You don't need to know CSS. There's no JavaScript at all, nothing. It's all Python. So all you need to do is write a little bit of Python and say go, and then you have an app. And that app is an interactive app. So I can click here. You can see I have these 2 apps deployed for version 0.19, which is the latest version. You can have different versions. I can now jump to that app. This is all launched by Kubernetes, hosted by EC2 right now. But everything is Kubernetified, right? If you want to say that. So there's a Helm chart that says how to launch H2O, one that says how to launch driverless, how to launch this and that. All these pieces, Steam, we have a launcher system that lets us launch driverless and H2O in the cloud. So here under engines, you can see who has what engine running. And you will see that I have one open source and one driverless running. So this is my H2O big data recipe backend that I have running. And if I click on it, you can actually see that it's H2O 3, and it is a 2-node system, just to show that it's distributed, and it has these CPUs that are not doing much right now. And I also have a driverless instance here. And that was the one that had to do the work earlier to build these models. And one of them here is the one I took the screenshots of for these the crazy features that you saw with the 7-way interactions. Okay. And just to let you know, this is if you want to visualize the scoring pipeline, for example, like what do the features look like? The original features are on the left. The ones on the right are the transform features. And you can see, it takes me a while to zoom in here on my MacBook, but there are a lot of little features created, right? And this is the whole pipeline. So it takes these original features on the left, turns them into target encoding or weight of evidence, string concatenation, whatever. It does all these outputs. And this pipeline is exactly what open source gets as the row by row conversion pipeline from driverless. So this is literally the visualization of the mojo that is run in open source. There's no shortcuts, no approximations, nothing. And you get an auto report and other things that say what happened and so on. But in short, let's do a live demo because we don't have that much time. So let's see which one is it here. Is this the one that's still starting? Yeah, it's still loading. So let's say I have one started. This is a Kubernetes instance. So once it gets started, I can just say I want to make a new experiment, right? And I can say live demo. And now it says, oh, I need to have a space or something, and no spaces in the name. Now I can choose my driverless engine, and I can say I have one running already. Or I can say I want to start a new one. Let me say I want to start a new one. I can say AI new, blah, 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 right? So you just say about how many cores you want, how much memory, how much disk, and so on. You say launch. And this is how you launch Driverless AI in the cloud. It's all taken care of for you. You don't need to download Docker images and, copy them around and do all this stuff. It's basically the next generation platform, where we take care of everything, but it's in your cloud. It's not always software as a service, right? It can be, but doesn't have to be. We don't offer a software as a service for you right now. We only offer that as a demo, as a demo trial place. So this demo instance that you're seeing right now here, this is hosted for you so you can play with it. But once you sign up for it, you want it, then you get to run it on your own machines, in your clouds, wherever the clouds are, or on your premise. So the data stays with you, and we don't see it, and Google or Amazon doesn't have to see it either, right? You can do this on premise. We sell you the software to run this whole. Now, let's not wait for this to happen. Like you can imagine, it will start at some point. So once you have it, let's say you want to have a demo. Let's say you have one of these instances up of Driverless AI. So there will be another one showing up soon once it's launched by Kubernetes. It takes a minute or two. I can select H2O 3 and Driverless that I just did earlier. These are my servers that I have running, that I launched through this system. Now I just need to provide the path to the training data. And that's usually something that both open source and driverless have to see, right? So if I take this path here, then it will fetch this right now live, and it will show me the columns and everything. So I can say I want to predict the target. It is classification, and I want to drop the ID. That's something that you can do. Now you can say, well, what about fold column? What about, changing the type? There's more one could do. This is just our app, right? This is all built in Python. Each one of those things is one line that says, make me a checkbox with this, make me a checkbox with that, pull down with this. So this is just to show you that you can build an app. And sometimes something goes wrong. This was because this instance probably wasn't up long and I was up all night. So I need to start it freshly. Sorry about that. And this is only a, what should I say, a artifact of our newness to the cloud. So let me do this again. Oh, here, see, now we have two of those. This is starting, this is running. So let me take the one that is running right now. And since this was just refreshed, it should be fine. So let's run it again. So it connected properly this time to the driverless server. And that's the one that I showed you earlier. So it's also been running overnight. And it already has an experiment that I built on that data set. And it actually has two. So if I take the RATSI NIHO experiment, then that would be the one that Driverless AI, let's see if I can find that real quick. So here it should be the Driverless AI Big Data Recipe instance. this guy should have a Razzi Niho or something. Yeah, this guy, okay? So this is the experiment we are now going to use. And, or I can say, no, make a new one. So let's just reuse this for now, and then I'll show you how to make a new one in a second on a smaller data set. So this one will now reuse an experiment. So you can actually run experiments yourself on the data set in driverless, just like before, like you've been doing for years on driverless, and then just use this experiment to create the feature engineering for open source. So once you have an experiment you like, you can now connect it up with open source, right? And this is H2O, GBM, random forest, XGBoost, AutoML. You have different choices. You can set the number of trees. I'll just do, let's say, 20 trees or 19. I don't do cross-validation, but I did that for the other one, so it was a little bit. This one will be faster, and I don't want to reset the cluster so that we have still stuff in there to show you in the meantime. Does this look good? Yes, looks good. I'm going to run 19 tree GBM. No early stopping, but with 19 trees, you're not going to overfit. We just want to compare the accuracy with 19 trees with the original data and with the augmented data. So now you can go to H2O3. You can look at the models. And you see the previous models I built overnight, but now you see the 791. It's numbered, right? This is the latest one. And if I do a refresh, you see it's training. See, 20 trees. And oh, we said 19, it's already done. Okay, good. So now we can go back and it should say, okay, I did it. I got a 74.7 AOC. Let me make that bigger again. And the 74 AOC is the original data model. And now we created these extra features because we reused this model from driverless here, the 5A88. That's just the UID, so you know which one it is. And now it uploads that driverless mojo to open source, makes the features based on it, makes extra 27 features based on target encoding. And now it should be running another model here. If I go list models, it should show me another model after the 791. That's going to come soon. And we can also probably see the water meter pumping at some point. And this is just Kubernetes provision, so that we only gave it something like 7 cores each or something. So it's not going to be all green, but it's, you know, this is all like our learning phases still. We don't know how many resources to allocate for the demo instances and so on. But you can imagine if you had this on premise, you would run this with all cores, you know, no limitations and so on. And when this is done, oh yeah, here it's done. So it built another model with 140 features total instead of 130 original features. So it did 117 plus the extra 27. It made these 144 features and it got a 78 accuracy. So right now what you saw is basically just open source building 2 models by reusing a existing driverless model. And you can also see the driverless variable importance itself, but we don't show a score because it's not really meaningful to look at the score of driverless here. But you could still do it, right? You can still go to driverless and look at the score of that experiment. You just have to know that this was, we don't have a test set, first of all, and second of all, it's only a validation score on the sample, right? We uploaded a sample. So what's the point of looking at a score of a sample? It's not really meaningful. So that's why we don't show it. But really, what you should focus on is the H2O GBM on the full data with the original data and then the transformed data. So let's do another one. Let's see, how does it work? I need to click on the plus. Doesn't react sometimes. Okay, fine. I'll refresh. Here we go. Let's do a credit card demo. This has a preloaded template, and all it says, see, this guy is still starting. So the cloud has, because I'm using maybe too many driverless or H2O instances already, it's still looking for resources somewhere. Sometimes it takes 5 minutes or so. It depends on your overall system. So we probably are somewhere here we are too stingy, and I'll tell the team that we should like unlock more nodes for this demo instance. But you can see here, this was already pre-filled because we had one of these templates. And the templates actually are all created here in our GitHub repo, right? This is the GitHub repo where we're building this big data app. And you can see here a credit card template says here, this is the target you should use, drop this and so on and do these settings. So all of it can be configured. And there is also sparkling water configurations where we have, similar stuff. It's almost the same, but it's slightly different. And there's definitely work ongoing how to run sparkling water pipeline. Here is Spark, you can see that, how you run everything. So there is cool stuff coming. That's all I can say. Now, if you go back here, let's do a credit card where we want to predict whether somebody will default on their payment next month, okay? And now we'll say, train a model from scratch because it doesn't have an existing model. It has to train one, so it doesn't even allow you to choose one. And now I'm going to say, just go and run. And now we will see, I'll just do defaults for everything. So it's fast because we're running out of time soon, but it's all perfect. So now we go to Driverless AI, and first we see that's already done, 76. Now we go to Driverless AI. It should now be building a model here, syncing. Yeah, this guy will now be building a model on the credit card data set here, default payment next month. And whatever this does, it's done 1/110, so it's super fast. It's like time one, accuracy one. It's the worst possible model you can build in the fastest amount of time. So it's not going to be good. And most likely it won't even find any new features. It might just return the original features because they're quite good. If you have no time, why should you invent a lot? Just use the features you have. So in this case, it used the exact original features, nothing to improve on. And it said, well, here we go. That's it. So see, this is the pipeline. It does nothing. Original transformer for most things. Some things are like done here, but not a lot. This doesn't mean much. String concatenation of marriage is still just marriage. So it's kind of useless, a 1D interaction. So yes, it's basically doing nothing. And now, of course, the score should be the same, right? It should be, roughly speaking, the same. So that's just noise here, the last digit. But you can see pay 1, pay 2 was the original features that mattered, and it's still pay 1, pay 2. But now it's has an underscore in the front with a number. That's the number of the feature created by driverless. So this is the different view of the same thing, and it happened to not help. So it doesn't mean that this recipe will always make it better. It depends on what driverless does, right? If you run it with the fastest possible settings, or on a wrong size sample, or the data has no signal at all to engineer, then this will not magically just make a better model. But it certainly can, just like in the case you saw earlier. You can also import a larger data set. So let me run this again here. I say new experiment. I just want to show you that we can run on a bigger data set too. Oh, now the other one is running too. So we could now use the new driverless, okay? The new cluster I just started, or the single node driverless. We don't launch clusters of driverless yet. There's no need here. The point is to run this on a subset. So this is the 8 GB data set. And again, we pull in real time the first few megabytes. We can now predict whether the flight will be delayed. It's classification. And we have the departure time and the scheduled departure time. So if you take the difference, you know the answer, which is why we need to drop the actual departure time. And now it connects to driverless, and we say take only 100 megabytes out of the 8 gigabytes, okay? And again, you could configure the settings and change all that, but for now I'll just say go, and now it will actually run on the full airline data set and pull that into open source. Where is the open sourcing? Water meter. You should see this getting a lot busier. But again, it's only using something like 7 physical cores on each machine because of the way we launch it through Kubernetes. So this is not typical. It will be even faster with the actual production version. So if I now go to models, this is the wrong cluster. I used a new one, I think. Oh, no, it's not. I said defaults. I said delete everything in H2O and start fresh. So now it's uploading the data to open source because it's 8 gigabytes, right? And now it should start it, yes. So let's see when it starts building a model. Doesn't have a model yet. Yeah, here we go. So by default, we delete everything in H2O because once it's done, there's not much value in having it around other than to show people. So sometimes we just delete. Here we go. So now it's building trees on this 8 GB data set. And you can see H2O3 does it one tree at a time. And you know what's funny is you can actually already see the production mojo or the pojo, like the actual model's production code as it's training, right? Here you see the Java code. So H2O is really all about productionizing your models. And even as it's training, here is the production code for the current model. And you can imagine, yeah, there's nothing that's too big, right? This is just a small 2-node cluster. And it's now done, I think. So if we go back to where is this guy here? Yeah, it did a 68 AOC, and now it's sampling 2% for use in driverless. And so driverless soon will get the 3% sample handed over from open source to make its model. But then that will take a while and so on. So you can imagine for the demo today, I think we saw what we needed to see, but every model that you run, oops, let's see if this works. I see, not yet. So we're still working on the app so that it becomes easier to use, but this is not the big data recipe. This is just the app. So don't worry about that for now. There are definitely, here we go. This was the credit card experiment we just ran. So there was no boost. And then there was the BMP that I showed you earlier where there was a massive boost. But this is just, yeah, as I said, this is just one way of seeing the results, right? And if you have other ideas like how you want to display it or what else you would want to see. So the download Mojo button is grayed out still because we haven't actually given that to you yet, the connection of the 3 Mojos, but that will come soon. And then you can also see the configuration and you can rerun it. But yes, please give us your feedback on any questions you might have. And there is ways to see, you can even look at the all the cloud activity from a command line, like what is running right now. And I can look at the logs for a certain instance. So let's say this instance here, what is it doing right now? And this instance number here is really just a number that you see at the URL at the top. So it's very easy to use this stuff. And the binary that we used here is H2O binary. Here at the beginning, that's just a file that sits around here. That's a 60 megabyte static binary, a Go binary. So it's very easy to run anywhere. Okay, cool. So I think I'll hand over for questions. And I think I can see on this other screen. Can they use any machine learning algorithms from the open source Python ecosystem? So the question is, where do you want to use Python? If you want to use Python in driverless, absolutely. So you can say, I want to make features that optimize my PyTorch or fast.ai, machine learning learner. So then you take a fast AI recipe and you let driverless figure out the best features for that. But then when you get that Mojo back, that Mojo for this purpose here will only do the feature engineering, right? So then you have the best feature engineering for a fast AI neural net, let's say. But then you give it into H2O AutoML on the open source side, and it will not have a fast AI model with Python. Now, if you want to do it, of course you can. Then you just stay in driverless, right? That is what the whole point is. Like you can give it a terabyte data set and say, run it in driverless. And you can do that. Like there is nothing stopping you from batch streaming 50 kilobytes at a time of a terabyte that sits on disk somewhere and just process it and learn over time how to, make a better model. So yes, you can do anything in Python, but you wouldn't do this with this big data recipe where we use H2O3 as the backend, because that's the fast backend that in the end gives you Java production artifact. Fast AI or PyTorch and others will not necessarily just give you Java production artifact you can put in production, right? That's the benefit of doing it in H2O. And yes, we can use H2O for NLP-like sentiment analysis. Both H2O 3 and Driverless have NLP capabilities. So this could definitely be done, no question. Are there any other questions? I'm trying to see where I need to look. If not, then thank you very much for your attention. I think we ran out of time. And please go to our website and try it out yourself. It's H2O.ai. Thank you very much. Have a good day.